Hello. In the next two videos, we're going to look at forces for objects that are resting on ramps. This is the hardest part of the ramps unit. It's not necessarily hard because there's math in there that you've never done before, but it is the most involved. You have to go through kind of a lot of steps. Now, the steps are usually pretty much the same from problem to problem. So once you learn what steps to go through, this shouldn't be too much of an issue, but it is one of the tougher things that we will do this year. I will be upfront with you about that. Before we get to forces on ramps, I want to do a little bit of math review. What we're going to be focusing on here is math that involves angles that are inside triangles. So as you can see, I have this big triangle here. I have a label right here that this angle is 24 degrees, and then I have some other right angles in this triangle. This is supposed to be the right angle, but you can probably tell it's a little bit slanted, the symbol at least. And then I have some angles that are labeled A, B, C, D, E, and F. Our goal for this is to figure out, based on what you're given, just that this is a 24-degree angle and that these are right angles, what the measures of A, B, C, D, E, and F are. This will be good warm-up for the math that we're going to have to do for forces on objects that are on ramps. We're going to start by figuring out angle A. And in order to figure out what angle A is, we have to remember a fact. And that fact is that the angles in a triangle always add to 180 degrees. If you look here, I have this little mini triangle right here. Okay. Matter of fact, you might even say it's similar to the overall triangle. And the reason it's similar is because I just dropped a straight line right down here from the hypotenuse down to this side, this leg. So if this is a 24-degree angle, then 24 plus this 90-degree angle plus A must equal 180 degrees because the angles in a triangle add up to 180 degrees. 24 degrees plus 90 degrees plus A equals 180 degrees. I can solve for A by simply subtracting 90 and 24 to the other side. So 180 minus 90 minus 24 is 66. The measure of angle A must be 66 degrees. I can figure out angle B due to something else that you learned in math class, and it has to do with an angle that looks like this entire thing right here. If this is kind of like a little pivot point here, and you have a line that intersects that pivot point, if you measure an angle from one side of the pivot all the way to the other side, that must be 180 degrees. And the angles that make up this, if there's multiple angles that get added up, they're called supplementary. So I know that A plus B plus, so I have this angle A right here, I have angle B, and then I have this right angle. So A plus B plus 90 degrees must equal 180 degrees. And again, that's because those are all supplementary angles. You can tell from the geometry that those angles must add up to 180 degrees. So we know that angle A is 66 degrees. We're looking for angle B. And we know that there's a right angle in there, and all those add up to 180 degrees. So again, we do 180 minus 90 minus 66, and angle B ends up being 24 degrees. Interestingly, that's the exact same angle that I started with down here. That's the important part for what we're going to do with ramps, but we're going to keep going and figure out angles C, D, E, and F as we go. Angle C, we can use the same sort of justification. Clearly, if this is a pivot point here and I'm measuring this full angle, the sum of this right angle and angle C have to be has to equal 180 degrees because those angles are supplementary. So again, because C plus 90 degrees, that's the 90-degree angle right there, equals 180 degrees because those are C and the 90-degree angle are supplementary. Therefore, C must be 90 degrees. Angle D, interestingly, we know it's actually going to be the same as angle A because, again, we have a right triangle here. The right triangle has angles that we know so far of 24 and 90 degrees, and we're looking for the measure of the other angle. When we did angle A, we already had angles of 24 and 90 degrees, and we were looking for the other angle. This is literally the exact same problem. So angle D is the same as A, therefore D equals 66 degrees. We could even say the same for angle E. It's going to be the same as A because this is just the overall big triangle. 24, 90 are the angles that we know so far, and E is up here. So the same logic applies. For angle F, there's a number of ways that I could do this, but I'm going to use the fact that, let's see, we said D was 66 degrees, E is 66 degrees. We're going to use the fact, this supplementary fact that we keep using. For angle F, we know that, here's our pivot point, this whole thing has to be 180 degrees, therefore D and F are supplementary. So D plus F equals 180 degrees because they're supplementary. Since D is 66 degrees, F must be 114 degrees. Okay, so a little bit of practice, a little bit of warm-up with angles. Now, again, the most important angle that you need to be able to realize is this one B. All the process that got us up to angle B is important. We're going to move now to actually talking about forces on ramps. Okay, the numbers that those angles will come back in a little bit. So here's a scenario. A wooden box is placed on a frictionless ramp. The ramp is inclined at an angle of 30 degrees with respect to the horizontal. What is going to happen to the box? Which way will it move, and how will it move? Well, we're told it's a frictionless ramp. I think you can envision that this box is going to slide down the ramp. And it's going to slide down the ramp in such a way that it accelerates, it picks up speed, it speeds up. It slides down the ramp with acceleration. In other words, it accelerates down, or it has a non-zero acceleration as it goes down the ramp because no forces hold it back. It might be a different case if there was friction on the ramp, but there's not. There's no one holding it, there's no ropes attached to it, nothing. So that's pretty standard. We can envision what's going to happen, but here's where it starts to get a little weird if we want to start maybe like drawing a free body diagram. If we use our standard coordinate system, x to the left and y up, so x horizontally, y vertically, that's not going to work out so well. Because remember, we need a coordinate system so that we can draw a free body diagram and then eventually find net force equations and talk about the acceleration. If we make a coordinate system like this, the box is not just moving in one direction. It would actually be moving in the positive x direction. As it moves down this way, it'd be moving in the positive x direction, but also the negative y direction, because it'd be descending and moving to the left. Now, that by itself isn't a problem, but if you think about it, then you would have two different net force equations that both have acceleration terms, and then you'd have the object accelerating in two different directions, and there'd be this angle that you have to throw in, and it would just be really, really confusing. It would be very difficult to deal with. So instead, because we don't want the box to accelerate in two different directions, because that, take my word for it, is going to be very messy, we can fix this situation. We can fix it so that the box only accelerates in one direction. We're going to do that by manipulating our axis, by tilting our axis so that it aligns with the surface of the ramp. Like that. Here's the x direction, here's the y direction. So we're going to tilt our axes. We now have x parallel to the ramp surface, and y is now perpendicular to the ramp surface. Why can we do this? We've never done this before. Well, we've never had something that is accelerating kind of like a diagonal fashion before. So we haven't had to do it. This might look weird to you, but remember that there's no rule anywhere that says our axis always has to look a certain way. The only rule with an axis is that x and y must be perpendicular to one another. Nothing says x has to be horizontal and y has to be vertical. That's just what usually ends up happening. Okay? It doesn't have to be like that. So we're going to get to a free body diagram pretty soon, but before we do that, let's think about the forces that are acting on the box. We know that it's on a ramp. That's kind of important. So it's in contact with a surface. Therefore, there must be a normal force acting on it. Therefore, the normal force, if you remember, always points perpendicular to the surface the object is in contact with. If the normal force always points perpendicular to the surface that the object is in contact with, here's the surface, perpendicular means at a right angle, the normal force from the ramp on the box points like this. If you look at your axis, that's the positive y direction. Okay, so the normal force is going to be in the positive y direction. Great. The fact that we tilted our axis means the normal force now lines up with the axis. Let's see if the weight, that's the other force on the box, does the same thing. We know that weight, or in other words, the force of gravity, always points straight down. Is that lined up with our axis? No. That means that the weight is sort of in the, if you tilt your head and kind of look, it's sort of in the positive x direction, but also sort of in the negative y direction. Okay? So it's somewhat, didn't mean to write it there. It is somewhat in the positive x direction. In other words, there's a component of weight that drags the box down the ramp, but it's also in the negative y direction. There's also a component of weight that holds, or part of the weight that holds the box down on the ramp, make sure it doesn't go flying off. So we have a force that is not exactly lined up with our axis. What do we do? You've been trained for this. You know what you're supposed to do here. In this situation, you must break that force up into components that are in the positive x and negative y directions. So in other words, you have to make it so that the force of weight, the weight of the box, the force of gravity on the box, does point straight down, but we need to look at it, we need to look at the components. And the components are going to be in the positive x direction and the negative y direction. Okay? We're not changing the force of gravity on the box. Okay? We're just looking at it through breaking the force up into components so that they align with our axis, so that eventually we can look at the different parts of the weight that pull in different directions. Another way of thinking about this, and I might have mentioned this just a second ago, we need to find the parts of the weight that are parallel to and perpendicular to the ramp itself. Okay, we need to find the components that look like this and this. And again, the whole reason we're doing this, okay, we haven't even drawn a free body diagram yet. I'm just kind of prepping you for the fact that we are going to have to draw the one, and therefore we are going to have to do this sort of thinking. And the whole reason we're doing that is so that we can talk about the accelerations in different directions once we've got the net force equations down. So the first thing that I'm going to do is I'm going to redraw the picture over here. I'm going to make it kind of big. You don't have to draw a picture like this, but I find that it really helped me to understand when I was first learning this and even first teaching this, why the free body diagram ended up looking like it did. Here's our box. Here's our axis. We'll start drawing the actual free body diagram in just a minute. I know that this is a 30-degree angle over here. Okay? For my free body diagram, I'm going to label this box. I'm going to have my axis. And normal force is in the positive y direction. Force of gravity is straight down. Now, I just got done saying I need to break the force of gravity up. I need to align it with my axis. That means if you look at the force of gravity, it's kind of in the positive x direction, kind of in the negative y direction. I need to draw in my components. Those components are going to be the force of gravity times either cosine or sine of theta, just like any other force that you break, or any other vector that you break into components. The issue is we need to figure out which one is which. Which one is fg times cosine theta, which one is fg times sine theta. In order to do that, we need to figure out where this 30-degree angle shows up in my diagram. And that's not obvious. So that's why we did the math at the beginning with the triangles, so that we can mathematically show which of these angles is the 30-degree angle. I'm going to add something to my picture over here. I'm going to add a line going straight down. Okay? Since it's a line going straight down and the bottom of the triangle is flat, horizontal, I know that this must be 90 degrees. And therefore, since this is 90 degrees and this is 30 degrees, and all the angles of a triangle have to add up to 180, the sum of these two angles right now is 120. 180 minus 120 means that this angle right here must be 60 degrees right now. If you look on your free body diagram, this is a line that points straight down. This is a component of the force of gravity that is parallel to the ramp surface. Here's the ramp surface. Here's a line that's straight down. This angle right here is the 60-degree angle, but that's not important. Okay? We don't care where a 60-degree angle goes because we weren't given in the initial problem an angle of 60 degrees. We were given an angle of 30 degrees. We want to see where the 30-degree angle shows up. I'm going to add one more thing to my drawing. I'm going to add a dotted line right here. It doesn't have to be dotted, but I'm going to choose to draw it that way. That dotted line is perpendicular to the ramp surface. If it's perpendicular to the ramp surface, that means the angle between the ramp surface and this dotted line is 90 degrees. If this much of that angle, that's 90 degrees from here to here, is 60 degrees, the remainder must be 30 degrees. That's similar logic to what we used before. Before, what we actually said was this whole entire thing is 180 degrees. So this must be 90 because it's perpendicular to, the dotted line is perpendicular to the ramp surface. We had 90 plus 60 plus something equals 180, which means that this must be 30. You also see these components must be perpendicular. If this is a 60-degree angle, this is a 30-degree angle. On your free body diagram, you will then put the theta symbol because you now know that this angle is the same exact thing as the angle that you were given initially. Okay, we're getting there. We're about halfway there. We've got a couple more jumps to make. We've still got to come up with the names for these components, but getting this angle was probably the most important thing. We've got to come up with names for these components. This component, you'll notice, is adjacent to where the angle. It's directly next to the angle itself. So if it's the adjacent component, adjacent makes you think of cosine, and as a matter of fact, this component is Fg cosine theta. Fg, the force of gravity, times the cosine of theta. Here's the original vector. Here's the here's the component of that vector that has a cosine theta term attached. Which means, if you were to imagine that this component, this dotted line up here, was down here, and it makes a right angle with this component, it would be the opposite side. Opposite makes you think of sine. So this component is named Fg sine theta. And I say named, but what I really mean is that's how you would calculate how big these components are. So I've got Fg cosine theta and Fg sine theta. I've figured out how to calculate those components, which is important for writing the net force equations in just a little bit. The trickiest thing, because now we're going to move on to the net force equation in just a little bit, the trickiest thing is figuring out where theta goes. If that confused you, go back. All we did was we figured out where another 30-degree angle was and saw that we had a corresponding angle in our free body diagram. So it must have been 30 degrees. That's where theta goes. That's the hardest thing to do. If you can do that, the rest of this is pretty straightforward. It's very similar to all the other force problems that we've done in the past. Sometimes I also have people that have issues remembering where theta goes, okay? They don't want to go through all the math. I recommend you go through all the math, but I have a couple little tricks. If you're drawing a free body diagram for a ramp question, again, this is just for ramp questions, not just for any old question that has to do with components. This is specifically for ramps. Theta appears between the force of gravity and the component of the force of gravity that is perpendicular to the ramp surface. Here are my two components. This is the one that parallels the ramp surface. You can see that right here. Here's the component perpendicular to the ramp surface. Theta is between FG and that component. And since that's where theta goes, in other words, the component perpendicular to the ramp surface, what I'm really trying to say, that's also the component that gets the attached cosine theta. Okay, so that's one way to remember where theta goes and which component this is. Okay, theta goes between FG and the component that's perpendicular to the ramp. And that component perpendicular to the ramp is the cosine theta one. One last way you might remember it, and this is kind of like the lowest level of remembering, we used to say, when we did components of things, that the x component, you found it by using cosine theta, the y component, you found it by using sine of theta. In this case, that's not true. Look at the x component. This is the component in the positive x direction, and it has sine theta attached. This is the component in the negative y direction. It has cosine theta attached. So this is a rare case where cosine and sine switch. Okay? You can remember it like that if you want. It's the lowest level of remembering it. I would prefer that you figure out why cosine and sine switch, but as long as you remember that there's something a little weird going on here and that cosine and sine switch just for ramps in this one special case and also a couple other cases that you might run into, that's good enough. Spelled switch wrong. There we go. Okay. Cosine and sine switch. That's good enough for a Regents level. Okay. Now that we figured out how to break the weight into components, we've got our all the way filled out free body diagram. By the way, this is what I'm ultimately going to be checking for. This is helpful. I'm not going to require it, but it is highly recommended. Now let's write the net force equations for both directions for this box and determine the acceleration of the box. Let's start with the x direction. You'll notice that in the x direction, there's only one force, Fg sine theta. And as we know, net force equations are always equal to max. F net is equal to ma. So I know that Fg, the force of gravity, is the same as m times g, the mass times the acceleration due to gravity. So I'm going to make that switch. So I have mg sine theta equals ma. And the reason I did that, I know I don't have numbers here, but I want to show you something a little bit interesting. Notice now that I have an m on both sides of the equation. What do you think happens if I divide both sides by m? It cancels out, and I'm left with ax equals g sine theta. In other words, what this is trying to tell me is that the acceleration of the box down the ramp is equal to the acceleration due to gravity times the sine of the angle. So very interesting. The acceleration does not depend on mass. This is really neat. We can prove this in class. We can take objects that have different masses, put them on a frictionless 30-degree incline, and they will all have the same acceleration, regardless if they're a tenth of a kilogram, 1 kilogram, 10 kilograms, whatever. That's really, really cool. We could even figure out the exact acceleration because we know what the acceleration due to gravity is. We know what little g is, 9.81 meters per second squared. We know what the sine of this angle is. We know the ramp angle is 30. The acceleration on the ramp of an object on the ramp must be 4.905 meters per second squared. We could adjust that one of two ways. We could adjust it by somehow finding a location where G is different, such as the moon or a different planet, or maybe going up like higher in the atmosphere, or by adjusting the ramp angle. That's a little easier, and we should get a different acceleration. But no matter what we do in this one particular case, where we have an object on a frictionless ramp, we see that the acceleration is not dependent on the mass. That is really, really neat. What we've done there, by getting down to this stage where ax equals g sine theta, that I'm kind of putting in this dotted box, that's called deriving an equation. We just derived an equation for the acceleration in this one particular situation. It's situation dependent, so it's not something that shows up on the reference tables, but we used our basic physics knowledge to come up with an equation that describes a certain situation. That's what deriving is. And that's a really important skill to have as a physicist. Moving away from that, let's do the net force in the y direction for one other little revelation. In the y direction, we have the normal force in the positive y direction and a component of the force of gravity in the negative y direction. Notice that just Fg is not going to fit in because it's not in just the x or y direction. So I have Fn minus Fg cosine theta equals MAY. Now, I think it's a pretty good bet that this box is not going to suddenly start accelerating up off the ramp. I bet it's also not going to sink down into the ramp. It's not going to accelerate in either of those directions. Therefore, in the y direction, the acceleration must be 0. That leads me to this. If that's 0, I can add this to the other side, and the normal force must be equal to the force of gravity times cosine theta. And that's actually an interesting result. I could also write it like this if you want to, but I think the point's a little bit lost there. We have gotten so used in most of our situations to saying that, well, we always know that the force of gravity, Fg, is equal to m times g, mass times acceleration due to gravity. In a lot of our free body diagrams, in a lot of our situations, we've also gotten used to saying Fn equals Fg, or Fn equals mg. The normal force is equal to the force of gravity. Look at this. It's not in this case. We know that by plugging in an angle for cosine theta, cosine is restricted to being between 0 and 1. So we know that by plugging in an angle, that's going to make this side here, that's going to decrease this side here. What that ultimately says is that the normal force is equal to a smaller number than the force of gravity. The normal force is not equal to the force of gravity here. Okay, we've gotten so used to saying that, but that's not something that always happens. The normal force is equal to a component of the force of gravity here. So Fn and Fg are not the same thing. They don't have to be. Don't think that they are. In a lot of cases they are, but they don't have to be. So normal force does not equal weight in this scenario. Again, this is one of the hardest forces topics, one of the hardest topics we do all year actually. Figuring out this, the fact that this angle goes right here and how to draw the free body diagram, that's a little bit tricky. If you didn't understand it, go back and rewatch it. We'll also have plenty of time to try it and practice this in class, so if you really do have questions, feel free to ask me. I'm more than happy to help. It is tricky, but you will get it. I have full faith that you will understand this. We're going to do some slightly more complicated ramp questions in a little bit, so maybe you'll even work it out there. We're going to add in some more forces in the next video. Bye.